Hello and welcome to this snapcast looking at the chemistry of benzene. Benzene has a formula C6H6, and a considerable amount of time of this snapcast will be spent looking at the structure of this, which we'll see today is represented by a hexagon with a circle in the middle. Any molecule that has one of these, a benzene ring in its structure, belongs to a family of compounds called aromatics. This is the study of aromatic chemistry. So called, you can see in that word aromatic the word aroma, so called because they are quite smelly compounds. And we'll be looking at a small number of these aromatic compounds that you see here. In terms of sources of benzene, most benzene is sourced from crude oil. Benzene can also be produced by a process called reforming. As the name perhaps suggests, reforming is a process that essentially changes the shape of a molecule to change it into something more useful. An example of reforming can be shown using hexane, which is the formula C6H14, an alkane. We could also look at a cycloalkane called cyclohexane, C6H12. We could also look at heptane, C7. All alkanes have twice as many hydrogens as carbons plus 2. 2 7s are 14, plus 2, 16. If this undergoes reforming, it produces C6H6. Now we've used 6 of the 14 hydrogens, so that leaves 8 hydrogens, and we have 4H2 then as well produced. That's hexane. This chemical here, cyclohexane, which looks like this, or is represented by a hexagon, and each carbon there is a carbon at each of the corners of the hexagon, and each carbon has also got 2 hydrogens attached. I'll just show them here, but the others are hydrogens as well. 6 carbons and twice as many hydrogens, 12. It's called cyclohexane. It can undergo reforming to produce benzene, C6H6. We've used 6 of the 12, so there are 6 hydrogens left. So in this case, 3H2. And heptane, well, it would form C6H. Now, one of the hydrogens on the benzene ring would be replaced in this case by a CH3 group. So we've used 5 and 3, 8 hydrogens of the 16, leaving 8. So there'd also be 4H2 produced there. You don't need to know the conditions required for reforming, but certainly be able to remember these examples, or to be able to recognize these as examples of reforming if given in a question. What about the uses and the toxicity, the dangers of benzene? Just a few quick points. Benzene is a colourless liquid with a sweet smell. It's volatile, in other words it evaporates very quickly in air. It dissolves only slightly in water. It's highly flammable. It's formed both by natural processes and human activities. It's used widely and probably features in the top 20 chemicals for production volume. There are quite a number of different industries that use benzene. It's used at some stage in the manufacture of many plastics, resins, nylon and synthetic fibers. It's also used in the manufacture of some types of rubber, lubricants, dyes, detergents, drugs and pesticides. As well as being produced from crude oil, it's produced in some natural processes including volcanoes and forest fires. Since it's found in crude oil, it'll also therefore be found in fractions of crude oil such as petrol, diesel, paraffin, and it's also found in cigarette smoke. What about its dangers, or the danger to you if you're exposed to benzene? Research has shown that benzene is carcinogenic. It's a carcinogen, or it causes cancer. With exposure from less than 5 years up to 30 years, research has shown individuals dying of leukemia. Long-term exposure may affect the bone marrow and therefore blood production. And even short-term exposure to high levels of benzene can be dangerous. can cause drowsiness, dizziness, unconsciousness, and can even in extremes cause death. I'm going to go through these as quickly as possible with you, and you can pause the slide if necessary. I just want to pick up the key points. Benzene was only discovered in the 19th century. In 1825, Michael Faraday discovered benzene, first to recognize its presence. It was a little while later that Kekulé, I think there should be an accent over this, Kekulé was the first to come up with a satisfactory structure for benzene. They had become aware that the relative molecular mass of benzene was 78, that it consisted of 6 carbons and 6 hydrogens, and as Kekulé and others tried to connect these in a straight chain and try to figure out how the hydrogens were connected, they clearly ran into difficulties because there simply wasn't enough hydrogens to fill up all the bonds of the carbon. But Kekulé apparently dreamt up this idea, a bit like a snake's tail, of taking the chain of 6 carbons and putting them into a ring. And he overcame the problem of the valency of carbon and hydrogen by having alternate double and single bonds as you go around the ring. Now, as we'll see, the Kekulé structure was not right, but it was a very good start. Let's look at 3 bits of evidence, and you need to know all 3 of these, that disprove the Kekulé structure for benzene. So this is the proposed structure by Kekulé for benzene. Alternate double, sure this is coming out well, alternate double and single bonds as we go around the ring, C6H6. Well, if benzene had indeed double bonds, carbon-carbon double bonds, like ethene, it should undergo an addition reaction with bromine and should produce a colourless product, and as a result decolorize bromine water. Benzene does no such thing. Benzene does not undergo an addition reaction with bromine, or indeed does not undergo addition reactions in general with nucleophiles. Now, the second bit of evidence, part of this has not come out in the slide production here. So let me just create an extra page. Now, if we take a look at an energy level diagram like this, where this is the energy, or better still, the enthalpy, and we're going up in enthalpy here. Now, you will recall that chemicals like to have the lowest enthalpy they can, and this will encourage them to react if they can produce chemicals with a lower overall enthalpy. Now, if we look at the reaction of C6H, not 12 but 10, this is cyclohexene. It's got 1 carbon-carbon double bond. Now, if we carry out the hydrogenation of that compound, we will get this compound. Remember, we've got a carbon at each of these corners, and each carbon additionally has 2 hydrogens. It's got a formula C6H12, and it's known as cyclohexane. Now, if we take the level of the cyclohexane there, the enthalpy change for this reaction is minus 120 kilojoules per mole. Now, this is not to scale, unfortunately, but if we take a look at a similar molecule, cyclohexadiene, let's say with a double bond here and a double bond there. In other words, it has the formula C6H8. It's got 2 carbon-carbon double bonds. When we look at its enthalpy of hydrogenation, it's exactly twice this figure. Now, it's not to scale, unfortunately, as you can see. It should be twice, the gap should be twice as great. I haven't the room to fit this in, unfortunately. But this comes out to be exactly twice at minus 240. Now, if Kekulé was right, then his structure is C6H6, and it's a hexagonal ring with 1, 2, 3 of these double bonds. And one would reasonably have expected that the enthalpy of hydrogenation would have been 3 times that figure, and therefore minus 360. Well, it didn't turn out to be minus 360. In fact, it turned out to be only minus 208, which left a discrepancy or a difference of 152 kilojoules per mole. It was less exothermic. Now, the reason that it would be less exothermic would have to be down to bonds within the benzene molecule being stronger than predicted by the Kekulé structure. When benzene undergoes hydrogenation, it does indeed form this product C6H12. So the discrepancy has to lie on the left-hand side of the equation. It doesn't lie with the hydrogen, because this involves 1 mole of hydrogen, this involves 2 moles of hydrogen, and this involves 3 moles of hydrogen. One can isolate the discrepancy, therefore, to be something to do with the benzene structure. And this figure 152 represents what's known as the delocalization energy of benzene. Benzene is a more stable structure than predicted by the Kekulé structure, which accounts for the fact that 152 kilojoules of energy, less energy, is released from the exothermic hydrogenation of benzene. Looking at the third bit of evidence, it comes from X-ray diffraction. X-ray diffraction studies pass X-rays through the sample, and these X-rays bounce off and hit a photographic plate, and this can be used then to find the distance between the adjacent atoms. Now, if Kekulé had been right, a carbon-carbon bond is longer than a carbon-carbon double bond, and they should have found 2 different carbon-carbon bond lengths. They didn't. They found only 1 carbon-carbon bond length, and in fact it was found to be intermediate in length between the carbon-carbon single and the carbon-carbon double, a bit like this in other words. We could represent it as somewhere between a double and a single. It was this scientist, Linus Pauling, who in 1931 came up with the modern picture of benzene. He's the father of resonance theory, hybrid orbitals, electronegativity, and valence bond theory. In a separate video cast, I've taken a fairly detailed look at the structure of benzene. We've looked at hybridized orbitals, and I'm not going to look at it in any detail at this point. If we take a look here at the electronic structure of carbon, carbon has a total of 6 electrons. 2,4 is its simple configuration. In a more complex configuration, it's written as 1s2, 2s2, 2p2. And in this other more detailed video cast, I've taken a look at this. This is a quick summary. What happens is one of these 2s electrons is promoted up here, and we have therefore a 1s2, 2s1, 2p3 setup. Now this would allow for 4 electrons to enter, which would actually happen in the case of CH4, and it accounts for the structure of the bonding in methane, CH4. Now, in order to account for the structure both in ethene and in benzene, we have to look at the hybridization of orbitals, and what's happening here is this orbital, the 2s orbital, this orbital, the 2px, and this orbital, the 2py, they come together to create what are known as sp2 hybrid orbitals, and they produce 3 identical sp2 hybrid orbitals. You notice that the 2pz does not get involved in joining or merging with those others. It remains separate, stays as was as the 2pz. These 3 hybrid orbitals here account for, as you can see with these blue lines, the bonds that connect between the carbons and the bonds that go out to the hydrogens here. And they all lie on one flat hexagonal plane. As a result, all 6 carbons here and indeed all 6 hydrogens coming out there are all on the same flat plane. Benzene, therefore, is a planar molecule. But what about the 2pz that doesn't get involved in merging with the other orbitals? Well, this is it here in each carbon. It extends both above and below that flat hexagonal plane. And there's one of these for each of the 6 carbons. Now we could look at these merging a bit like in ethene, above and below, and indeed that does happen. But it happens to the one adjacent on both sides, and to these ones here, both above and below. It happens all the way around the ring, that the 2pz orbitals on each carbon merge, and therefore the structure of benzene is better represented as a flat ring, above which we've got this gravy ring area that represents where the electrons are mostly found, both above and below. You'll see that represented better in textbooks, I'm sure. So this is the kind of arrangement we have in benzene. The blue here represented by the blue here, an electron in each of these hybrid orbitals here, and then the reds, this is one orbital both above and below, and that's the 2pz orbital that has not got involved in merging with the others. It's these that merge both above and below the ring. Now because each of these, if we go back to this, I'll shade one of these 2pz orbitals in. There's one electron in that 2pz orbital, and there's one in each of them, each of these 2pz orbitals for each of the 6 carbons. So there's a total of 6 electrons associated with those electrons of the 2pz. And those 6 electrons, where are they found? Well, they have a tremendous range of movement. At times they'll be found above the plane of the ring, and at times they'll be found below the plane of the ring. So those are delocalized electrons. The benzene ring then is a flat structure with high electron density sitting above and below the ring, and that helps us to understand much of the chemistry of benzene. And that's what's being shown here. We could think of the 2pz's on 2 adjacent carbons merging together, either like this one in 6 or like this one in 7. But in fact, as I showed you, they merge all the way around, merge into one another. So instead of having just 2 electrons that occupy this space here, and then 2 that occupy this space here, the whole lot merges both above and below, and the 6 electrons associated with those have tremendous range of movement above and below the ring. At times one particular electron might be found here, moments later it might be found there. Just pause this and have a look at the questions and the answers. So why does benzene possess 152 kilojoules per mole less energy than predicted? That's really enthalpy. It's more stable than predicted, and this represents the fact that it's got 152 kilojoules less enthalpy. On an enthalpy scale, if this is enthalpy, chemicals want to be as low as possible. Kekule's structure was putting it up here somewhere, whereas the actual structure is lower down in enthalpy terms. And the difference between where Kekule's structure would be and where it actually is this. Here's the answer. The missing energy, called the resonance energy, important term to know here, is attributed to the overlap of p orbitals, those 2pz orbitals. And due to the resonance, a resonance means sort of going back and forward. The resonance in benzene. Why does benzene resist addition and prefer substitution? Well, it's because of the desirability of this structure, this resonance structure or delocalized electron structure. It's a particularly stable structure, and if benzene was to undergo an addition reaction, it would mean giving that up. If benzene were to undergo addition, resonance would be disrupted, and this would render the structure less stable. Therefore, benzene prefers substitution. It can manage to keep its ring in the middle, and you simply replace, let's say, H with a B or whatever. So it prefers substitution to addition, but it will, under the right circumstances, undergo addition reactions. It'll take a lot more energy, though. Why does benzene possess 6 bonds intermediate between carbon-carbon double and carbon single? Well, according to the resonance, the bonds are not carbon-carbon single bonds. They're not carbon-carbon double bonds, but a hybrid of the two. And this is why the X-ray shows that up. Now, the reactions of benzene, and this is the most important, electrophilic substitution reactions. What's an electrophile? Well, an electrophile is an electron deficient species. It will mostly be positive, so we'll come across nucleophiles like the nitronium ion, NO+, unusual electrophiles like the BR+, CH3+, plus being on the carbon. We'll come across the acyl one as well, where we have double bond O, some R group or alkyl group here, and we have a positive charge in that. And there are others as well. Electrophiles are, in general, harder to prepare than nucleophiles, but electrophiles will attack what is a very electron-rich species, the benzene ring. In contrast, a nucleophile like Cl- or indeed NH3, these are nucleophiles, if they try to approach a benzene ring, because the benzene ring is electron-rich and they are essentially electron-rich, one will repel the other, so benzene will not undergo nucleophilic type reactions. In contrast, because these electron deficient species are positive, benzene will react extremely well with electrophiles. So pause again, just take down the information here. We're going to be looking at monohalogenation, mono meaning one. We're looking at situations where one of the hydrogens, remember, if I show one of them, there is actually hydrogens, of course, at each corner there. For simplicity, we generally don't put these hydrogens in. But monohalogenation is where one of the hydrogens is replaced by a Cl or a Br or an I. We'll be looking at nitration, which involves the so-called nitronium ion, NO2+. We'll be looking at alkylation, where we're producing the carbocations like CH3 plus or C2H5 with a plus on the carbon. And we'll be looking at acylation, which is this species here. Here's a summary. You should pause and have a look at the information here. In terms of halogenation of the benzene ring, how do we create the electrophile? The electrophile in the case of chlorine is going to be Cl+. Well, here we need to make use of a so-called halogen carrier. The halogen carrier does the following. We think of a chlorine molecule like so. This is just a simple Cl2 molecule. You notice we have a shared pair of electrons here in the middle. A halogen carrier like, for example, aluminium chloride. Aluminium chloride has what we call an incomplete octet. Aluminium has only 3 electrons in its outer shell, and in this structure AlCl3, the aluminium is only surrounded by 6 electrons. It therefore has an empty p orbital. And that empty p orbital will accept this non-bonding electron pair in the chlorine, and this causes this molecule to split like so, creating on this side a chlorine missing an electron, therefore it has a positive charge, and on this side we'll get that chlorine coming across here, forming a dative covalent bond to the AlCl3. Of course, it brings across a charge as well, having an extra electron. It took both of these electrons bonding electrons here, and that has a minus charge. So when we combine Cl2 with AlCl3, we create two ions. We create, importantly, the Cl plus electrophile, and we also produce AlCl4 with a minus charge. This acts as a catalyst and will be regenerated again later in the reaction and can be used over and over again. The reaction requires heat. It requires a halogen carrier, which can be, that should say AlCl3 there, AlCl3 or FeCl3. In the case of FeCl3, iron being in the D block has got empty d orbitals that can do something similar to aluminium, accepting a non-bonding electron pair. So they, in stripping away the chlorine there, create the electrophile. In the case of nitration of benzene to form nitrobenzene, we use concentrated nitric acid and the catalyst sulfuric acid. The sulfuric acid reacts with the nitric acid, both in concentrated form, to produce the NO2 plus electrophile. And that replaces one of the hydrogens on the benzene ring, so that we get nitrobenzene. It's a replacement or a substitution reaction, so electrophilic substitution. In the case of alkylation, where we're putting in an alkyl group such as CH3 or C2H5, etc., again we can use aluminium chloride. And if you look at this bottom left-hand corner again, if you imagine that to be not ClCl, but CH3Cl, then you can see how you could produce a CH3+. Or indeed, if this chlorine on the left here was a C2H5 bonded to Cl, you could see how the very same process would produce a C2H5 with a positive charge on the carbon. And in that way we can get various alkyl groups with a positive charge on the carbon, an electrophile or a carbocation, which will readily attack the electron-rich benzene ring. With acylation, down on the bottom here, we're talking about having an acyl chloride, looks like so. And again, if you think of the halogen carrier AlCl3 or FeCl3 coming in, again, if it strips this off, this chlorine here, taking the chlorine together with both electrons in that carbon-chlorine bond, it's going to create a positive charge on that carbon as a result. And that will replace the hydrogen on the benzene ring with a COCH3 or a COC2H5 group, etc. The other product, of course, will be HCl, and that will regenerate the AlCl3 to be used over and over again. Let's pick up some of the details of this then. I've lost that slide again. Okay, chlorination of benzene. This is what I was showing you earlier. We're looking at this image here at the moment. Here's the halogen carrier, aluminium chloride. Aluminium has only got 3 electrons in its outer shell, so even when it has bonded with 3 chlorines, it still has only 6 electrons around it. It has an incomplete octet. And this pair of electrons here in the chlorine are non-bonding valence electrons. They will form a dative covalent bond with that aluminium, and when it strips off, as shown here, creating this chlorine on the left, which is shown here, that has lost one of its electrons and therefore has a positive charge, and that is the key species. That is the electrophile. The aluminium chloride is behaving as what we call a halogen carrier. As well as that, we'll get AlCl4 with a minus charge. This is summarizing the process. The aluminium chloride then pulls away this. It creates that Cl plus species. These curly arrows in blue track the movements of electrons. This has 6 electrons in it, remember, from the earlier description of the structure of benzene. Now 2 of those electrons come out to form a bond with this chlorine. That's this bond here. you notice that the ring has been broken. It is only a positive charge because although 2 electrons have come out of the ring there, those 2 electrons are shared still with the ring. This carbon of the ring, which is part of the ring, has still a share in those 2. But when something agrees to share a pair of electrons, it effectively is down 1 electron, which explains the single positive charge in the middle of the ring at that point. Notice that the broken ring should break representing 2 sides of the ring. Equivalent, the ring has 6 sides, so if you break the circle equivalent to 2 parts of the ring, that's in terms of proportions the way you should think. Now at this stage, this is an unstable intermediate here, and what will happen now is, as you can see down here, the 2 electrons of this bond both go back into the ring again. Now one of those already belonged to this carbon, but what's happening is it's getting both of them now, which explains why we lose this positive charge here in the product. And the H comes off here. This H comes off without its electron, comes off as a H plus. And that H plus strips away, remember, this is the AlCl4, with a minus charge. This H here will strip away one of these chlorines, for example this one, to give HCl and regenerate the catalyst AlCl3. I see here there's CH3s. This was meant to be methyl benzenes, just to be consistent all the way through here. There is some significance to the position the chlorine went onto the ring relative to the CH3, but we don't look at that in the A level. In this particular case, the chlorine is specifically shown going on to the carbon opposite the methyl group that was already present. When you have more than one group on a benzene ring, the first position is called position 1. You then number around the ring clockwise or counterclockwise, so that the second group is on a carbon with the lowest number you could give it. In this particular case, it doesn't matter whether we go clockwise or counterclockwise. It'll still end up on carbon 4. So we started with methyl benzene. We've put a chlorine on carbon 4, hence it's called 4-chloro-methylbenzene. Methyl benzene has an old name, by the way, you may come across, still used. Toluene. You've heard of TNT. The T there is for toluene. There's toluene again, CH3. TN, trinitro. And if you have 3 nitro groups on there, I believe, could be wrong, I believe they are in these positions. You've just made dynamite. Trinitrotoluene. Why is it so explosive? Those N's will produce lots of this wonderful stuff with a really strong bond, nitrogen. The H's will produce waters with lots of good strong OH's. The C's will produce CO2s with plenty of these good strong C double bond O's. And look at all those oxygens built into the structure to help it undergo reaction. Nitration. This is the mechanism here. The overall equation, we start with benzene, which we now use this symbol for, and we react it to produce nitrobenzene. It really doesn't where we can also draw the benzene ring like this, as if it were lying on its side, so to speak. Either of these is correct, and it doesn't matter which of these particular corners you put the NO2 group onto. You could put it on here if you wish to represent the product like that, or on here, which typically is the case. Okay, so let's go for this one here. This is the product, and you need to know the reagents. What are the reagents? And you must say concentrated HNO3 nitric acid, concentrated H2SO4 sulfuric acid. You need to know the temperature. The temperature must be kept below 55 degrees C. Why is that? Because of the risk of getting multiple nitrations, and I say risk because as we get more nitro groups on here, it gets to be more and more like TNT. Well, not trinitrotoluene, but it could be trinitrobenzene, which would again be explosive. And apart from that, if we're looking to make nitrobenzene, we don't want to form dinitrobenzene, so we maintain the conditions below 55 degrees C. This is the mechanism. We need to consider how the NO2 plus the nitronium ion is formed, and you will need to memorize the equation. There are different forms of this. This is one of the ones you could remember. The HNO3 reacts with sulfuric acid, 2H2SO4, and it produces the NO2 plus electrophile. Organic chemists quite often circle the charges, plus H3O plus 2HSO4 minus. The sulfuric acid has two roles in this reaction. It acts as a solvent for the reactants being the nitric acid and the benzene, and it also acts in this particular role we see here, reacting with the nitric acid to generate the nitronium ion. Remember, these curly arrows like this one here trace the movement of electrons. 6 electrons in this ring, 2 of them come out to form this bond here. But those 2 electrons belong to the ring, and they are still associated with the ring. They are between this carbon, which is part of the ring, and the NO2 group. That really should stop about here. It's gone a bit too far, that particular broken arc there. The positive charge can be shown there, but is more often shown here somewhere. Then what happens, this arrow is missing. What happens then, this is an intermediate here, these 2 electrons go back into the ring, which is why we have no charge in the product in the middle. The H has come off without this hydrogen's come off without its electron, it comes off as a H plus, which is what we see here. But of course that H plus then can combine with the HSO4 minus to give us back the sulfuric acid. So in that sense, the sulfuric acid is behaving as a catalyst in helping nitric acid generate the important electrophile, the NO2 plus ion. As you will be aware, the detailed practical behind the preparation and the purification of nitrobenzene is on your syllabus. You will have chosen a safer alternative to this. You will have carried out not the nitration of benzene, but the nitration of methyl benzoate to form methyl 3-nitrobenzoate. Okay, these are the steps that you will have carried out, or you need to know would be carried out in order to nitrate benzene. Step 1, and we went over these warnings earlier. Preparing first of all the nitrating mixture. You take the concentrated nitric acid in a large round bottom flask. You do not take a flask that just about fills the contents of your reactants. You need plenty of space in the flask, so a suitably large round bottom flask is taken. And slowly then you add 40 cubic centimeters of concentrated sulfuric acid. That's an exothermic process, and you need to keep cooling it during the addition by immersing it in a flask of cold water. Note that benzene is almost immiscible with the nitrating mixture, so it takes plenty of agitation there. Place a thermometer in this nitrating mixture and then add very slowly the benzene. And this should be added about 3 cubic centimeters at a time with plenty of cooling in between. And you do your best to make sure the contents are thoroughly mixed after each addition. And don't let the temperature go up above 50 degrees C in this particular case. In the case of where we're using methyl benzoate, we're dealing with much lower temperatures, of course. So I shouldn't be showing a beaker here. I wasn't able to get a drawing for you. This should therefore be your flask placed in a very large beaker with cold or iced water. So now you've added the nitrating mixture completely, and you're ready to begin refluxing it for a period of time, refluxing it gently. So when all the benzene has been added, you fit a reflux condenser to the flask, and you can get an electric heating element, something called an isomantle, which connects the electricity. It's better to use a non-flame source for heating. And you maintain the temperature at 60 degrees centigrade for 45 minutes. During this period, the flask should be withdrawn from the bath from time to time and vigorously shaken in order to break up the nitrobenzene layer, which would otherwise float on the dense acid layer below. So if we've got two layers that really aren't mixing very well, that's going to slow down greatly the rate of reaction. Step 4, after then completion of heating, you pour the contents of the flask into a large excess of cold water. In the case of the methyl benzoate, we use crushed ice. And it says when you do this, the nitrobenzene will sink to the bottom of the beaker. So the nitrobenzene product will be down here. But it'll be there, of course, with concentrated sulfuric acid. Since it's a catalyst, it'll still be there. There'll be unreacted organic chemicals and inorganic chemicals as well, so it'll be contaminated. You stir the mixture as vigorously as possible. Why? Well, this is to remove as much of the acid. The acid will be much more soluble in the water than it will be in the product. Next, step 5, you decant. You're just simply turning the beaker on its side and pouring off as much of the top layer as possible, making sure you don't lose any of the lower layer where your product is contained. And transfer the residual, what's left, in other words this stuff at the bottom, into a separating funnel. So what's at the bottom of the beaker then will be transferred into a separating funnel. You run off and retain the lower nitrobenzene layer, so there'll still be some water there. It's not in the decantation process. You can only crudely separate the aqueous and non-aqueous layers. So at this stage then you run off and you will retain the lower, more dense layer in which you have your product. You then return that nitrobenzene layer back into the funnel, having of course removed the top aqueous layer, and you shake it vigorously with an equal volume of cold water. Here we're still trying to get rid of any acid that might be present with the product, your nitrobenzene. And you wait and allow the layers to separate out completely, and once again you run off the lower layer and keep it. That's your product layer. And again you return it back to the funnel again and wash it this time with equal volumes of sodium carbonate solution. The intention of the sodium carbonate is again to any acid that's there will react with the sodium carbonate. We'll get lots of effervescence as a sign that there is indeed still acid present. Because CO2 is released in the process, you must be careful if you have a stopper on here. Once you've had shaken, remove this periodically. Give it a couple of shakes, remove the stopper to let the CO2 be released. If you don't, it's going to blow out on its own. Some people like to put the stopper in and turn this upside down and then use the stopcock here to release the gas. And you would keep doing this until when you add the sodium carbonate you don't see any more bubbling or effervescence, and that's a sure sign then that all the acid has been removed, until there's no evolution of CO2. Step 7, you separate the nitrobenzene from the sodium carbonate. So at this stage the sodium carbonate has reacted with the acid. It'll have formed inorganic products which are essentially soluble in the aqueous layer and insoluble in the nitrobenzene layer. So all the stuff you want to get rid of should be in the upper aqueous layer, and you separate them using the funnel. In step 8 you transfer it then to a small conical flask. This is the lower nitrobenzene layer. At this stage, with all the washings, there's clearly going to be some water present with your product. Now while we say that that non-polar doesn't mix with polar. Some of the water will indeed have got trapped in amongst the product layer. And indeed, you'll have lost some of your product in the upper aqueous layer, hopefully not very much. So the purpose of putting it in the flask now and sit there, you put in here, as you see, anhydrous granular calcium chloride, a drying agent, and you shake it until the liquid is completely clear. Whenever water is caught up in an oily layer, it tends to produce an emulsion, a cloudy emulsion. So as you shake it, it should get clearer and clearer. As those water droplets caught up in the non-polar methyl benzene layer are removed, it will get clearer and clearer, and you shake until it is completely clear. That way you've removed the water. This goes beyond the remit of A level, I would imagine. You filter then the nitrobenzene layer through a fluted paper. In most cases, just simply decanting off the product is considered satisfactory. Directly into a 60 cubic centimeter distilling flask down here. And now you're going to carry out simple distillation and collect your fraction over a very narrow temperature range. Anything coming off before 207 is to be discarded. Anything coming off after 211 is to be discarded. And that's, in doing it that way, you should have obtained very pure nitrobenzene. Note, after washing with sodium carbonate solution, it would be usual to wash with water to remove any traces of sodium carbonate. However, nitrobenzene tends to produce an emulsion if you do this, which takes a long time to separate. But again, that goes into more detail than is required. The key reactions here are summarized. These should be, of course, subscripts here. The dual role that I mentioned of sulfuric acid, it's a solvent for dissolving the key reactants, benzene and nitric acid. And it's a catalyst. It reacts with the nitric acid to form the nitronium ion. But you saw how the hydrogen ions generated in the reaction regenerate the sulfuric acid. And typical of a catalyst, it gets regenerated and can be used over and over. What we did in our particular experiment was, this is what we're required to do in schools, we are strongly recommended not to have benzene in the laboratory in view of its carcinogenic properties. We carried out a reaction with a relative of benzene. We used methyl benzoate instead. But the chemistry was very similar, just carried out at a lower temperature. Here we have a beaker in which we cool everything down. This time we want to keep the temperature not below 55 but below 5 degrees C. We cool everything down in here, and what we did was we obtained, well, this shows us what the product looked like at the end, but what we did was we made our nitrating mixture by slowly, as was the case earlier there with the production of methyl benzene. We mixed the sulfuric acid and nitric acid together with cooling, keeping the temperature below 5, and that takes considerably longer than in the case of benzene, where the temperature had to be maintained below 55. When we had the nitrating mixture prepared, we then started to add the methyl benzoate, again keeping the temperature lower. And when all that had been added, we left it to sit, I think, for 15 minutes. There was no refluxing necessary. So after 15 or 30 minutes of it sitting after all the nitrating mixture had been added to the benzene, or vice versa, we then added it to crushed ice, and when the ice melted, this is exactly what it looked like here on the right. We got these white or pale yellow crystals formed. It is worth just spending a couple of moments reviewing the key aspects of how you purify a product that is solid. In the case of methyl benzene, the product was a liquid, and we were using a separating funnel to carry out various separation stages, and then it ended up with simple distillation. Well, in the case of your organic product being a solid, as is the case with methyl 3-nitrobenzoate, then one's using melting point as a criterion for purity. And to purify it, one uses a process called recrystallization. You choose a solvent in which your crystals are soluble when the solvent is hot, but insoluble when the solvent is cold. Now, it's difficult to get such a solvent, and you'll never get the ideal case. It's likely that your product will be slightly soluble even in the cold solvent, so a certain amount of your product is going to be lost as a result of that. But where one requires reasonable purity, one has no choice but to suffer the fact that some of the product will be lost. In this particular practical, you use either ethanol or methanol as a suitable solvent. Emphasis on dissolving your product in the minimum volume of hot solvent, given that some of it's going to be lost as a result of a small amount remaining dissolved in the cold solvent. When it's dissolved, there may be small amounts of solid that didn't dissolve. Those would be impurities, and one should filter the solution at that stage through hot glassware using fluted filter paper, which accelerates the filtration process. The hot apparatus, hot glassware, avoids the solvent cooling and crystals forming actually in the neck of the funnel. That removes as the residue any undissolved impurities. You then let the filtrate, which is still a hot solvent, cool very slowly to room temperature. If it cools too quickly, as it cools, some of the impurities that would remain insoluble in the cold solvent will get caught back up again in the crystals as they form. So the slower it happens, the slower the cooling takes place, the less of that will happen, and the purer your product will be. Now, when it's cooled completely and slowly to room temperature, there still will be a little bit of your product dissolved in the solvent. You're unlikely to find a solvent in which your product is entirely soluble when it's hot and entirely insoluble when it's cold. So when it's reached room temperature, you should put it into an ice water bath to cool it even further and crystallize out even more of your product. And at that stage, then, using Buchner apparatus, a Buchner funnel, siphon pump or vacuum pump, you would then filter off your product, your crystals. You would dry them between sheets of filter paper, and then you could test the melting point and use the melting point to decide on the purity. If the crystals were not sufficiently pure, then you would have to consider going through the process of recrystallization again. Remember the formula for working out the yield, what's known as the practical yield. Sorry, I beg your pardon, the percentage yield. The percentage yield would be what you got in practice, in other words, the practical yield, over what you should have got in theory, which we call the theoretical yield, multiplied by 100%. So, for example, if you got 2 grams, when the mole calculations determined that you should really have got 5, and that comes out as a percentage figure, then it's 2/5 or 40% was your yield. You should be able to answer questions, suggest why the yield was lower than expected or why the yield was much less than 100%. I've already suggested some of them, like, for example, the fact that some of your product remains dissolved even in the cold solvent and is therefore discarded. Other typical answers would be that the reaction itself does not reach completion. The reaction produces side products, like, for example, instead of mononitration, you may get some dinitration or trinitration or whatever. Okay, let's move on. 2 other important types of electrophilic substitution that we've already touched upon. The idea of alkylation and acylation. These reactions are known as Friedel-Crafts reactions, where we use aluminium chloride to create the electrophile, which is either an alkyl electrophile or an acyl electrophile, such can be represented by C double bond O with a positive charge. Now, this is tremendously useful in synthesis, When you look at the structures of some drugs, you'll see that quite a number of them are based on benzene type structures. And it's great to be able to take a benzene ring and put either an alkyl group of any particular length or an acyl group on, and once you get these groups on, you can work with those and add other bits and build up your molecule and eventually get your drug or whatever it is you're trying to produce. So if one discovers in a particular plant a drug that has, or a chemical that has some pharmaceutical benefit, and having identified the actual chemical structure, one with a good knowledge of aromatic chemistry can begin to synthesize that through a series of steps. And you'll quite often find that you're starting by putting on OR groups or Cl groups, BR groups, acyl groups, and these are key reactions then in taking the benzene molecule and getting started on the journey to synthesizing a complex aromatic compound. Significance: electrophilic aromatic substitution reactions feature an electrophile replacing a hydrogen atom on the aromatic compound and can form a new carbon-carbon bond if done with an electrophilic carbon species. In other words, some carbon species with a positive charge. Such reactions were discovered in 1877 by Charles Friedel and James Crafts and are collectively known as Friedel-Crafts reactions. These reactions may be used to introduce both acyl, Friedel-Crafts alkylation, and acyl groups, Friedel-Crafts acylation. A little bit more detail on these reactions. First of all, the alkylation, where we're trying to put on, let's say, a CH3 or a CH3 CH2 or a CH3 CH2 CH2 CH2, etc. We want to put on a group like that. There'll be a positive charge. It'll have a carbocation. So in each case here, these will be electrophiles or carbocations. Taking a look at a simple case here, let's say we want to put on a simple CH3 group here. If we take a halogenoalkane, also known as alkyl halide, that has that alkyl group, so bromomethane or chloromethane is shown here, and it was the Friedel-Crafts, the catalyst here is aluminium chloride. It does what we saw earlier. It strips away that chlorine. So where we've got that bond between the carbon and the chlorine, it strips it away, creating that, on this side, that alkyl group with a positive charge, carbocation, and then that OR plus, that electrophile, remember, is better shown as a circle. It's got 6 electrons. 2 of those 6 electrons come out to form a bond with this OR group, the CH3 in this case, etc. Again, it's better that these are shown as circles. And you'll notice that it does require reflux distillation. Reflux using anhydrous conditions. That's to say you must make sure that water is kept out. And there's a reminder. Here we're using the Friedel-Crafts catalyst FeCl3. We've got our halogenoalkane, alkyl halide, or Cl. Look how this bond, this shared pair of electrons in the OR-Cl bond breaks, both going to the right, creating this very important species here, OR+. It's producing FeCl4. It's a minus charge. But once that H+ leaves the molecule, the benzene ring, it will strip off one of the chlorines of the FeCl4, regenerating the FeCl3, as is shown here, stripping off this hydrogen. This hydrogen comes off without its electron here, that electron going back into the benzene ring to complete it. Again, I prefer that these should be drawn as circles. Pause and look at this in your own time. The acylation is similar. We've got the benzene ring. This time we're using OR, C double bond O, Cl, an S-al chloride. You might be more comfortable with me putting CH3 in instead of R, but R is put in there to indicate that it could be any alkyl group. And what happens here is, the key thing is, it's this bonding pair of electrons here, that when the FeCl3 comes in, it strips this off like so, producing FeCl4 with a minus charge. But more importantly, over here it's producing the RC double bond O with a positive charge on the carbon, since the carbon here has lost both electrons, or it's lost its share in these electrons here. Should be shown as an X, I suppose, there. And then that RC double bond O with a positive charge, electrons come out to form a bond here with this. Now the conditions, first of all, if we were just representing this as a balanced equation, we'd write RCOCl. We'd use FeCl3 or AlCl3. We'd reflux, and again, anhydrous conditions. We have to make sure that water is kept out. And the product that we form, the H will come off, and we will get then on there C with the double bond O, and then whatever that R group is as well. Now that's a ketone type of arrangement, because we've got, essentially, put it in simple terms, we've got that kind of arrangement. And this group here is known as a phenyl group. So if this R group was CH3, it would be known as phenyl ethanone. Phenyl ethanone if that was CH3. Just picking up the mechanism a little bit more. It's this bond breaking, both electrons going to the right. And so, as I've shown you there earlier, you can put on the C double bond. That group, I put it on there a moment ago. It could have gone on. It can go on any of these positions. You could put it on here as well if you like. Plus you get HCl then, and it also regenerates your AlCl3 or FeCl3 if you wish. Next, let's take a look at the reduction of nitrobenzene. Reduction involves, we can use this as a symbol for reduction. We're talking about nitrobenzene, which looks like this. In order to bring this process about, we use concentrated. Make sure you know whether it's concentrated or dilute. Simply saying nitric acid may not get you the marks. You use concentrated hydrochloric acid and tin catalyst, SN for tin, it's used as a catalyst. What happens in fact is the tin reacts with the HCl and it produces tin 2 plus 2 Cl minus, and the key thing is it's acting as a reducing agent there. It's producing the hydrogen, and it's putting on in fact 4 H's. Sorry, but it's putting on, 4 H's are involved. We'll see why. It puts on 2 of the H's there in place of the O, and each of these O's needs 2 hydrogens. So in fact, there's 6 hydrogens altogether being used. Those 2 O's involved on the nitrobenzene each will turn to water, and that will give 2 H2O's. So you have 4 hydrogens in the 2 waters plus these 2 hydrogens, a total of 6. So you could write that as C6H5NO2, that's your nitrobenzene, plus 6 square brackets H, and that produces C6H5NH2 plus 2 H2O. and it goes by several names. It's known as aminobenzene, it's known as phenylamine, and its old name is aniline. The properties of phenylamine, well, it's a liquid and it boils at high temperature, 184 degrees centigrade. It's a primary amine, represented like that. It's a weaker alkali. Amines can be considered as based on ammonia, NH3. Remember, the nitrogen has a lone pair of electrons. And as you make amines, what you're essentially doing is you're replacing one or more of the hydrogens on the ammonia molecule. Ammonia is a weak alkali, and amines, seen as derived from ammonia, are also alkaline. Aliphatic amines are stronger alkalis than ammonia. This aromatic amine, phenylamine, is a weaker alkali than ammonia. It's a weaker alkali than ammonia, and let's see why. It's explained by the electron-rich benzene ring. Benzene rings are a very stable electron system, and our electrons are readily drawn into the benzene ring. So benzene rings are electron withdrawing. The opposite is true of alkyl groups. They're electron donating. Now, what makes this and ammonia alkaline is best seen according to the Lewis theory. According to the Lewis theory of acids and bases, a Lewis base, is a lone pair donator. And it's this lone pair that can be donated and accept a proton that makes it a base. The more available that lone pair on the nitrogen is, the stronger it will act as a base. In the case of phenylamine here, because the electron-rich benzene ring, because the benzene ring is electron-rich, it tends to pull on this, making it less available and a weaker base. If we compare that with something like CH3, CH2, NH2, in this case, an alkyl group is attached to the nitrogen with the lone pair. Alkyl groups are electron donating, and if they're donating electrons towards that nitrogen is going to be more inclined to give up that non-bonding electron pair, and that explains why aliphatic amines are stronger than ammonia, and the bigger this alkyl group is, the better in terms of making a somewhat stronger weak base. When we get to secondary amines, where we replace not just one but two of the H's with alkyl groups, they would be expected in stronger bases. And if we replace three, in the case of a tertiary amine, then even stronger again. Very important, the diazonium salts, the formation of azo compounds, which are brightly colored compounds. Back in the late 50s and throughout the 1960s, this was a revolution in chemistry, and students going to university to study chemistry very often went into a new faculty called color and polymer chemistry. Most of this science seems to have been discovered in that short period of time, because it then began to wane after the 1970s. So what about diazonium salts and azo compounds? Only phenylamine can form a diazonium salt. These compounds are used to make synthetic dyes. Let's see how we change phenylamine into a diazonium salt, a very reactive species that is only stable if maintained at low temperatures, and how we can take that marvelously reactive diazonium salt and very easily and readily convert it into a range of chemicals, including azo dyes. First of all, the formation of the diazonium salt. We use nitrous, not nitric, but nitrous acid. But nitrous acid is unstable, and it needs to be made, the expression is, made in situ. In other words, react it and make it there and then, where and when you need it. It's made by the reaction of sodium nitrite, with hydrochloric acid, concentrated hydrochloric acid, or moderately concentrated, did I say yeah, hydrochloric acid, and it forms nitrous acid, not nitric, nitrous acid, and sodium chloride. I should have indicated there as well. Must be made fresh at the temperature below 5 degrees C, that should say. Step 2, the phenylamine, or aminobenzene, or aniline, is reacted with nitrous acid to produce the diazonium salt. Temperatures kept low. Above 5 degrees centigrade, this will split up, break down, in other words. And the full equation is the phenylamine plus these two chemicals that generate the nitrous acid gives this chemical, the benzene diazonium ion. Notice got that positive charge on that, this specifically that nitrogen, and that's an ion. Going along with it there is the chloride ion. It also produces the water and sodium chloride that we saw on the previous page. So those are the conditions: keeping the temperature low, mixing it with sodium nitrite and hydrochloric acid to generate the nitrous acid. The temperature rises above 5 degrees C, then the benzene diazonium chloride decomposes to give off nitrogen gas. Now, because this chemical is so reactive, and in particular because it will react with nucleophiles, this is considered a very important chemical in synthesis. So here's our chemical that we're keeping below 5 degrees centigrade, and if we want to produce an azo compound like this, something missing from here, the benzene ring hasn't come out. Let's just put that in for you. So this is part of a benzene ring here. And this is phenol. If phenol is reacted with the product of the previous reaction, the so-called benzene diazonium salt, it reacts to form this chemical, which is a azo compound, and it's brightly colored. In fact, in this particular case, it's a yellow dye. It's not as complicated perhaps as it looks. What do you have to remember to draw the structure? Well, the phenol part on the right has more or less maintained the way it was, so there's nothing very much there. This bit stays, I guess. But the joining takes place here. What's happening is, I think you can see this triple bond, one of the bonds of the triple bond is coming around to form a bond between that nitrogen and one of the carbons. In fact, the carbon 4 here, if we call this carbon 1, 2, 3 and 4, one of the bonds of the triple bond N is coming out to form this bond, so it changes to a double bond then. So that's what you have to remember. Its proper IUPAC name, 4-hydroxyphenylazobenzene. If you were to, if the phenol was replaced by a chemical called naphthalene, naphthalene is actually just two benzene rings together like this. Naphthalene. If you were to use that instead of phenol, then you would get another azo compound, which is a red dye. While very reactive chemicals can be dangerous, when it comes to synthesis, very reactive chemicals are great. They act as stepping stones to produce other chemicals, and because they're reactive, it reduces the costs. Now here's in the middle here, you can see the diazonium chloride. Wonderful stuff because it's reactive and will readily change into a range of other chemicals. Here we see a repeat of the reaction we looked at a moment ago. It will react with phenol to form a dye, a yellow dye, an azo compound. But look what it does here. Just warming it with water will produce phenol. That's great. Warming it with copper cyanide will introduce the C triple bond N. And once you've got that, you can go all kinds of places. Once you've got the C triple bond N on, you can convert that C triple bond quite easily to COOH and get benzoic acid. Benzoic acid can be converted to an ester, etc., etc., etc. Here's it reacting with HBF4, and it's introducing an F onto it. We've got it reacting with an acid here, changing it back to benzene, taking an aqueous solution of copper bromide and introducing bromine to form bromobenzene. Copper chloride to get a chlorine on, chlorobenzene. Simply put, aqueous potassium iodide at room temperature will produce iodobenzene, and so on. So you can see, very valuable in terms of organic synthesis. A little bit on phenol then. Phenol, remember, looks like that, or can be represented, is that right, C6, yeah, C6H5OH. Pure phenol is a white crystalline solid that melts just above 40 degrees centigrade. It smells like disinfectant. Students are reminded of the smell of deep heat used by footballers for muscle injuries or to warm up the muscles. It has to be handled with great care because it causes immediate white blistering to the skin. The crystals are often rather wet and discolored, and the molten liquid boils at 180 degrees centigrade. Perhaps I should have said there, you've heard of TCP. Pretty sure that stands for trichlorophenol. So you imagine 3 chlorines on, I don't know where they are, perhaps they're on something like that. I believe that's TCP, could be wrong, trichlorophenol. The influence of the OH group. You should be able to liken or compare and contrast an aliphatic alcohol like CH3CH2OH, that's ethanol, with phenol C6H5OH. What's the difference? What difference is made by having an aromatic group attached to the OH versus an aliphatic group? The benzene ring becomes more reactive. The presence of that OH group makes the benzene part of the molecule more reactive, and that is good when it comes to organic synthesis. This results because of an interaction between the delocalized electrons in the benzene ring and one of the lone pairs on the oxygen. When you've got that COH bond, there are 2 non-bonding electron pairs on the oxygen. One of the oxygen lone pairs is donated into the ring, so you can visualize if this is the ring here, they are donated into the ring, and this increases the electron density even more around the ring, making it even more reactive, even more electron rich, attracting even more strongly electrophiles. It also helps the OH group to dissociate more. Now, when an alcohol can have acidic properties as a result of a weak dissociation where we get RO- plus H+, and the more this OH bond breaks, the more of this H+ you'll get, and the stronger it will be as a weak acid. So it also helps the OH group to dissociate more fully, explaining why phenol is a stronger weak acid than ethanol. We can use what are called pKa values to compare the acid strength. The bigger the Ka, the stronger the weak acid is, but when we turn from Ka to pKa, which is the negative log of the Ka, it's the other way around. A smaller pKa value indicates a stronger weak acid, and phenol has got a smaller pKa value than ethanol, and that indicates to us as chemists that it is a stronger weak acid. Reactions of phenol, well, it'll undergo combustion, producing carbon dioxide and water and releasing energy. Like most compounds containing benzene rings, combustion is hardly ever complete, especially if they are burnt in air rather than pure oxygen. Phenol tends to burn in air with an extremely smoky flame as a result, which is lots of unburnt carbon. Phenol, like other alcohols, will indeed undergo esterification. It only very slowly reacts with carboxylic acids, but it reacts satisfactorily with acyl chlorides. And here is phenol reacting with ethanoyl chloride, forming the ester phenylethanoate and hydrogen chloride. That completes this lecture, but it doesn't complete literally everything that you need to know about aromatic chemistry. There are two accompanying snapcasts, one that looks at 6 or 7 past papers from SIA, and then another looking at questions from other examining boards, principally AQA and OCR, and I strongly recommend that you look at those as well.